Thank you ever so much. Thanks to the organizers for having me here. It's good to be in Vienna. So I'll talk about what I've been working on. Is it possible to get lights on here at the front? It's better. Right, what I've been working on for the past sort of 10 years or so. So, we've heard from esteemed colleagues talking about exciting, interesting, and important things they've been working on. And then there's this stuff. There's this old saying that those who can do and those who can't write papers on dynamical subsets in iterated function systems. So I don't know if this is all that interesting or important. But what I want to tell you is what kind of things can you do with these things, or what is already known and what is not known, and then hopefully by the end of it, you'll have a feeling for whether you think it's interesting or not. So setup is as follows. I have an iterated function system. So that's M contractions on RD, iterated function system. And I assume that these maps are affine, meaning that each of them is of the form Ti plus Ai, where this is a linear map and that's a translation vector. And so what that does is, crucially, it takes a ball to a slug shape rather than another ball. So it doesn't uniformly scale. So that's going to be a big enemy. And throughout, I think I'll have to assume that they contract by at least 1/2. And I'm also assuming, for the most part, that they satisfy what is known as the strong separation condition. What that means is as follows. So whenever you have an iterative function system, it comes with an invariant set. I'll denote that by lambda. By invariance, I mean that if I take the image of this set lambda under all of my maps, then I get the set back. I'm assuming that you've seen this before. And then this set typically has fractal features, meaning that it looks like this. That's my lambda. And the strong separation condition means that these images are disjoint. I'll assume that for the most part, because it makes the thing that I'm about to say next a little bit easier to believe is well defined, namely. So whenever you have an iterative function system and the corresponding attractor and invariant set, you can code it using a space of sequences of digits coming from the collection, which are the indices of your maps in the iterated function system. So you get this sequence space, and then there is a natural map between the sequence space sigma and the attractor, which I'll call pi. And this map pi, I'll give you the definition. Again, I hope that you've seen it before. If I have a sequence of digits from this collection, what you do is you take the composition of the first n maps coming from that sequence, and you take the image of, let's say, lambda, let n go to infinity. It's going to converge to a point on the attractor. And I'll also give you a notation for this. This composition of the first n maps in a sequence, I shall also denote by that f, x, n. Right, okay, so now we have these two spaces. We have the attractor, the fractal set, and we have the sequence space. And we have a map between them, which under this strong separation condition, I can tell you, is going to be a bijection. And it's going to be continuous both ways. So it's a homeomorphism. And so, and then in the sequence space, we have the natural dynamical system, which is the shift map. And so then there is, on the fractal set, there is a corresponding dynamical system, which I'll denote by F. And what does this F do? It takes a point X from the attractor, and now because it's a point in the attractor, it has to belong to one of these images of the attractor under these maps F1 to Fm. And so the F of X is going to be what you get when you take the inverse of the map Fi and apply that to X when X happens to belong to the I's image of lambda. So these Fi's were linear contractions, and so then this is a linear expansion. It has these local definitions depending on which image of lambda you happen to be inside. Okay. And then, luckily, it happens to be, and this is assuming that these images are indeed disjoint, this map is well defined. It's a unique choice of Fi. And so then this map, which I said was a homeomorphism, is a conjugacy between sigma and F. So that's nice, if you like symbolic dynamics. I do. Okay, I think that's all that I wanted to say about the setup. So then what are these dynamical? So this is the setup of dynamical systems on iterated function systems, and then I want to talk about shrinking targets. So thank you to the organizers also for setting up Philippe before me, because what he was saying is a very nice lead-in to what I'm about to say. And I was paying very close attention at the start of his talk, and I don't think anything that I say is going to be in direct contradiction with what he had said. So that's very good. Right, so as we've seen, for a shrinking target, you have your dynamical system, and then you have some sequence of targets. I'll call them UN. And then you're looking at those points. I'll denote this set by RUN, R. These are those points in, so when I analyze things, I will often be looking at things in the sequence space, but the sequence space doesn't have any nice geometry. And so when I'm asking questions, I'm asking the questions in the subset of lambda, which has some geometry to it. So hence, I define things like this. So this is the shrinking target set. I have those points X, which at time n under the dynamical system hit the corresponding target UN. And this has to happen infinitely often. So that's the set that I'm interested in. And then for this UN, I can make many choices. And there's two choices that I will be making in particular today. One of them is to let UN be some ball of some radius X node and some, of a center X node and a radius Rn decreasing to 0. So X node is some point and Rn is some sequence. And the other choice that I will be making, and now this might seem unnatural, but it is not, is to take the images of lambda under some composition of maps. Okay? So here, X is a sequence on the sequence space, and Ln is some sequence approaching infinity. Okay? So these are shrinking because the radii are decreasing. And these are shrinking too, because this Ln is growing. I'm taking more and more maps, so this set becomes smaller and smaller. So this is also the image of the corresponding cylinder set from the sequence space, if you're more comfortable with that. So So here we have a shrinking target set up. And then the question is, of course, what about its size? So very helpfully, Philip already told you that this shrinking target set is the Lim subset of pre-images of these UNs like this. And this Lim subset of pre-images like this in my particular setting is going to be the union of all possible images of UN under compositions of maps from my iterated function system up to time n. So let me give you some more notation. This here means some word of length n from my sequence space. So I'm taking all possible images of words of length n from the sequence space and applying those maps to UN. And that's going to give me the pre-image of UN under my dynamical system F, the nth pre-image of UN under my dynamical system F. And so now this is typically, so even if UN happens to be the ball up there, even if UN happens to be the ball, this is typically not a ball, right? Because my maps are affine and they don't scale. So this typically tends to be something odd. Okay. So then the question is, I asked the same question first that Philip asked, which is, what about the measure of R? Now I said that I don't know if this is all that interesting, and I'll tell you now why I don't think it's necessarily all that interesting. The reason is that when you're doing this, the answer is always exactly as you would expect, or the things that you have to do are always exactly as you would expect, and then you just have to do them. And then, you know, sometimes there's some geometric complication while you're trying to do them. Sometimes it's a little bit non-trivial. Sometimes it takes you 50 pages to do. But even the geometric complications tend to be as you would expect. And then you just have to deal with it. So when it comes to the measure of R, we were already told how to do this, right? You want to prove some sort of a dynamical Borel-Cantelli lemma. And if you want the measure to be 1, so you have some sort of a 0, 1, I have nested sequences. So you have some sort of a 0, 1 law in the background. You know, if the measures of the target sets converge, then you're definitely going to have a 0 measure R. And if they diverge, then you have a question, am I independent enough to have full measure? And, you know, then you just have to show that you have enough independence to have full measure. That's all. So let me write that down. That if I want to, okay, I want to do some sort of a dynamical. So okay, so this is with respect to some natural measure. And now the measure that I'll be applying soon, it won't be an ergodic measure for the dynamical system, but we'll pretend. Okay, so some natural measure. And then what you have to do is you have to prove some sort of a dynamical Borel-Cantelli lemma. And so, you know, first question that you have to ask yourself, if you're in some setting, you have to ask, okay, is it true that the pre-images of UN have a measure so large that this sum diverges? So that's the first step. But now, if you have an invariant measure, then the pre-image does nothing, and so then you're just stuck with this instead. And so, okay, so then the condition you have to first check is if you want to know if your full measure or 0 measure, you have to check whether you diverge or not. So let's assume that we are in the setting where things diverge. Then you have to know So this is a question, first question. And then the second question is, am I independent enough? So Philip had very strong independence conditions. There was a proper independence. So the weakest, and this comes from sort of a Diophantine approximation in the world, the quasi-independence and average. It's like a weak independence condition which somehow controls the overlaps between the images, between the pre-images. And this is essentially from Diophantine approximation. As everybody knows, the rational numbers are the least random set, which is still random somehow. You have to look for weak conditions for independence. Right, so you have to check somehow. So, put it sort of mildly. So you need to control the size of intersections, the measure of these. Maybe more layers, maybe not just pairwise. Right, so in this context that I'm talking about, this iterated function system context, questions like this have been looked at by people. I'll mention names like Simon Baker and Demi Allen and Balazs Barani. But they didn't do this affine stuff. They did other kinds of setups. And so then I got swept up in the tide that is Simon. And we did this last year sometime. It came up in archive. Been published. So, okay, so I'm assuming that the Lebesgue measure of lambda is positive. Okay? And this is equivalent to, or this is a consequence of knowing that the sum of the determinants of the linear maps, the sum of the determinants of the linear maps is greater than 1. Then you know that you have positive measure for the invariant set. And why do I want to do this? Well, then I need to assume that all of these maps TI, these linear maps, are, we have multiple conditions that would be enough to satisfy what I'm about to say. And this is a pair of them. So if all of them are equal to some positive diagonal, the same positive diagonal matrix, that's one case, or they are all equal to some T node, which doesn't have to be a positive diagonal matrix, and we are on the plane, so D is equal to 2. The ambient dimension of the space is equal to 2. So for example, in these two settings, we can prove that for almost every A1 to AM and for every X from lambda, almost every Y in lambda is contained in the recurrent set where I'm looking at balls. The radius is chosen very carefully to be something like, for example, 1 over n times the sum of the determinants of the linear maps to the power n, everything to the power 1 over d. Not very important. So obviously what I'm trying to do with this radius is I'm trying to make that condition hold. And this becomes crucial because of some sort of geometric properties that are coming from the iterated function system. So this is how the maps scale. Obviously, they scale by determinant of pi, and so anyway, so that's why it shows up. And then this 1 over n is superfluous. Divergent is good enough. Have a class of such things. Statement clear, and is it correct? Yes. No, I don't. Sorry. Okay. Yeah, that's a very good point. Thank you. Thank you. I said I will almost all the time assume the sort of strong separation condition. And then I said that it's convenient for me right now because I'm about to define this map F. Okay, yes. So then I should have said they are overlapping in this case, very much so. And somehow that's the only case we can deal with, even. It's taken care of by this. So I know that. Yeah. So I have a lot of them. That's what this is saying. And then this is saying things can be too detrimental for me because I've taken typical translations. There's a lot of things that I'm sort of sweeping under the rug. But what you didn't ask, even though that's a fair question as well, is what do I do with the definition of F if I have overlaps, right? Because then I said that, oh, it's well defined because it's a unique choice of Fi, right? And now there isn't. So what then? But if indeed that is the case in here, and then I just take all of them. So instead of just take, it's like a multi-valued map. And this all makes sense in the sequence space without any question. The sequence space doesn't care about overlaps. Everyone's happy? Okay, what about everybody else? Okay, so that's the statement. Oh, that's one of the statements. But as I say, there were multiple. Now I want to say just one thing about the proof, two things about the proof. The first thing is, as I say, this is just to guarantee that the sum diverges. And then these two statements actually have a different proof. So this one is using, so what do we need to check? We need to check that these overlaps are not too bad, right? That's what I said we need to do. That's a geometric complication. Now, here we are, dealing with the geometric complication. The geometric complication is that, so we have these maps, and we're somehow wanting to show that these images of UNs are not too badly overlapping if you change n. And so the first strategy is to somehow show that they are definitely not overlapping, typically. Okay? Typically with respect to A1 to AM. That's the strategy that worked for the first case. And for the second case, you show that the measure of the overlap is not too large. Or indeed, the measure of the overlap, when also integrated over A1 to AM, is not too large. There's two different proofs for this statement. Okay, so that was that. So that's all that I want to say about measures in iterated function systems, measures of shrinking target sets in iterated function systems. So the next thing I wanted to talk about is dimensions of the shrinking target sets in iterated function systems. So once you're happy, convinced that you're dealt with the measure case, then you can ask, okay, what about the zero measure case? What is the dimension in the zero measure case? Right? That's the. What about the Hausdorff dimension of R? So at lunch 2 days ago, I asked, do we think that people here are comfortable with Hausdorff dimension? I was told yes. So I'm assuming that everybody's comfortable with Hausdorff dimension, but I'm happy to be told otherwise. Yeah, it was Dahlia. Let's not name names, okay? Let's not point fingers. Okay, nobody dares to say yes. I was wanting to express it in such a way that nobody would feel like saying yes. Okay, so even if you've never really worked with Hausdorff dimension, or if you're not sort of, you wouldn't know you wouldn't feel happy starting to prove the Hausdorff dimension result. You've probably seen enough talks about it to know that, okay, when you're dealing with the Hausdorff dimension, you need two things to worry about. The first one is the upper bound, which is given by some sort of a cover of the set. And then the second thing is the lower bound, which is trickier. Okay. So this knowledge is enough for today. So the upper bound, in the case of shrinking target sets. So as I say, everything with this business, everything always goes the way that you would think. So the first thing that goes exactly as you would think is this, the upper bound for the shrinking target set. The upper bound works like, oh, I hadn't written it down. Okay. The upper bound works like this. So your R, UN, is the limb subset of the pre-images of UN, right? Now limb sub, you can write it out, and Philip already did this. You can write it out like this. So it's the intersection of the union of the tail of the sequence, right? And so now what that means is that this is always a cover for your target, shrinking target set. This is always a cover. And indeed, if you are in the situation where you have to look further than this, then you're in trouble. So I'll tell you about one result where you have to look further than this, and that was tricky. Okay, so upper bounds are always obvious. So now the geometric consideration that you have to worry about in this affine map context is the following. So when you're doing covers for the Hausdorff dimension computation, you want to use covers of balls. But as I said, the iterative function system stretches things out, and so then what you're covering are not balls, but sets that look like this. And so then instead of covering sets that look like this, you need to cover them with balls. And so then, okay, so then there is something to think about. But this is all well known. So it just leads to this potential or this sort of a geometric object, which is called the singular value function. I'll not tell you the definition of the singular value function. I'll just tell you that it has to do with how to cover long sets like this. Yes.
There's no overlap.
Yes. Yeah.
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 These
You're right. You're right. You're right. You're saying I'm oversimplifying things. That's a fair point. So we aren't even able to compute the Hausdorff dimension of the lambda itself in all cases. Okay, there's lots of cases where we don't know what the dimension even is. So the overlaps are not the crucial point for the affine maps, but what is a crucial point is this. So the results that I will be presenting are all going to be of this form, where I'm assuming a typical choice of translations. To some extent, yeah. What's that? Some sort of... Exactly, that's it. Yeah. So I wasn't preparing this to be like a dimension theory talk. I want to focus on the sort of aspects of this which have to do with dynamical systems, but this is all extremely relevant. This is all extremely relevant, and there would be a second hour where I would tell you all that. I mean, we can also delay lunch. Okay. So yeah, so there is the computation for the Hausdorff dimension of lambda itself is with respect to where you have a typical translation is due to Kenneth Falconer, and he was the one who introduced this singular value function, which was it's a revelation, or somehow it was even ahead of its time in '88 when the paper came out, and there's a lot of deep theory that goes in. And there's lots of clever people who are working on the remaining cases. What if you don't have typical translations, like Balash and Mike Hockman and Ariel Rappaport and people like that. But yes, as I say, I will not talk about it. Talk about other things. And that is, I will tell you how to do lower bounds. So nobody knows how to compute dimensions of anything apart from counter sets, essentially. And so for this case, the lower bound strategy relies on finding counter sets which have a dimension which is close to that, as with many dimension computations. And so the goal is to find a counter set of sort of, and the structure of this counter set is going to be as follows, of predetermined fixed predetermined sparse returns. So I fix some subsequence nk, and I insist that my points return at exactly times nk and all of them, and then I get a kind of a counter set that I can then study the dimension of. Because, so one thing to note perhaps is that this shrinking target set tends to be dense in the ambient space, in this case the lambda, and so it's not very easy to put up measures on it. But when you take this counter set inside it, so obviously if you have returns at all times nk, then you have infinitely many returns. And this is a counter set, it's a compact set, which is inside R and inside lambda. And so then the dimension for this is easier to estimate from below because it's easier to put measures on this set. Right. So, so this is, I have some predetermined set of returns nk, and I take the counter set inside to be those points which return at exactly times nk for all k. That's what I've got. Now, so far what I've said is not in any way dependent on which UN I was looking at, but from now on, I will be looking at the second UN. So for this dimension considerations, the second UN is much, much easier than the ball because of essentially stuff like this. And so I'm now taking UN to be this image of lambda. Or this cylinder set. Now, if you think about it, if you have this as your target set, then what are these returns? They are, so I've already told you what the image of UN is going to be. It's going to look like this. I have all the possible beginnings of length nk in this case. And then I have this fixed choice f x ln. Okay. Okay. And then I have the whole of lambda, which means that I have all possible choices of sequences from here on. Okay. And so then, what does this look like in the sequence space? So what does this intersection look like in the sequence space in sigma? It looks like this. So I have the first, let's say, nk digits. Those are the j. I can choose freely. Then I have a fixed choice of digits. That's the x, l, and k. And then I have a free choice of digits again, because I have everybody here. Okay, so that's what this looks like, a single return. That's what it looks like in the sequence space. So now I'm insisting that I have exactly all of these guys. All of these guys are returns. So then what it looks like is that I just have, another time. This is my nk plus 1. I need to return. And then I have a free choice again. That's what it looks like in the sequence space. I have all these times which I've predetermined to be exactly the target, and then a free choice in between. Okay. And as I say, so this is where it's very useful for me to be looking at this target, second target, rather than the bool. I'll come back to that in a moment. Now, this is where another geometric complication arises, and the geometric complication is, and I'm being vague here, but somehow, so I'm having to look at these compositions of maps, right? And when I was covering with essentially with a union of a single return. But here I'm covering with an intersection of returns. Where I have all these times when I fix things. And somehow it would be much nicer for me if I was able to say, well, obviously I want these two things to be the same. I want the lower bound to match with the upper bound. And so it would be much easier for me if I could say that somehow this geometric quantity that I'm computing were multiplicative, because that would mean that if I stop at some point and I somehow forget what has happened in the past, I could start over. And the outcome would be just the product of those two things, what happened in the past, what happened in the future. But that's not the case for this guy. That's not the case. You want to hear why? Yeah, it's because, well, now I'm entering.
Which case are you
No, I'm in the arbitrary. I've left this setup. This was just the one statement. I have now moved on to arbitrary iterated function systems. Fine. Then you know already. Okay. So it has to do with this. Okay. So if you have two compositions of linear maps, one of them looks like outcome is like this guy is stretched like this and that guy is stretched like this, and then when I combine them, it just keeps on stretching, right? So this is a good case. Here's a bad case. If I have one map which looks like this and another map which looks like this, and I compose them, then things start to deform. So this is the reason why there's no product. You can't just take products of things, because it matters how do they match up. So this phi s never forgets. And that's a complication. Okay? So in vague terms, this is the complication that we have to deal with. That this phi s has a good memory and is not multiplicative. And now I'm about to state some theorems. But let me just mention that some people who've worked on this, well, I don't know, is there any so in this kind of iterative function system context, in the past, before the people that I'm about to mention, there's not so many people who have done these things. I've put down Reeve and Wang Wushu and Hill and Vellani, but Hill and Vellani didn't actually do iterative function systems. They did like Thorough automorphisms, which is close enough, but not exactly the same. Right, okay. So I need to determine what is my Ln. If I want to state a theorem, I need to determine what it is. So I'm going to say that this Ln is linear in n. So this has to do with how fast the measure of the target set decreases, which has to do with whether the sum converges or not, right? And so I want to be in the zero measure case. So I want this to be fast enough. So it turns out the linear in n is fast enough. And then x is arbitrary. And then I know that for almost every AI, the dimension of the recurrent set for this target choice of f x ln of lambda, this one, is given by S naught, where S naught satisfies the following. This limit as n goes to infinity of 1 over n of log of sum over all words of length n of this mysterious singular value function applied to the composition of fi composed with the target map when this is 0. Okay, and this is a kind of a pressure formula, like thermodynamics. Now, I said that the singular value function doesn't forget, and this is a problem. So we have to somehow control the multiplicativity of the singular value function. And so I'll tell you under which settings this formula actually holds. So this is if the IFS has a multiplicative singular value function, so if it is multiplicative or up to a constant. So this is due to me and Felipe from a while back. And then it was improved by Barani and Troshite, negative up to fixed length connecting words, whatever that means. And constants. This was Barani and Troshite. Then we improved it further. Everything else is the same, except we have bounded lengths connecting words. This is due to me and Limin and Mihao. Now this paper is a very sad story with this paper, because what happened is we'd been working on it for a while, and then I had a baby. Now you might think that having a baby is something that comes with pre-warning, and until you read the interview I gave to the Hello magazine. No, the baby just came a bit earlier than I had expected, and so then this project got to put on pause. And then in between, this paper came out, and so then we didn't, the stuff that we had wasn't exactly the same, but it wasn't different enough to be published as such. And so then we pushed on, and so we managed to do this bounded length case. And then, finished it up. And but then it's been getting sort of a very bad response from the referees. So, but then something good happened, which is that I went to this conference in Lumini, and Ian Morris was there, and I guess we both hoped that we would be going on nice hikes while in Lumini, but it was way too hot to do that, so we were stuck in the house, and so then we started talking about maths to each other, because what else? And so then Ian has a way of improving our result, but this is now with a question mark, because it has not been in any form properly written down. And so, okay, so if you add Ian to us, and essentially you add this paper to something that Ian's working on with Antti Käänmäki, you get every affine iterated function system. You can remove all of these multiplicativity conditions. So all that stuff that I was saying about, oh my God, things are very, very complicated, is actually not true. So maybe let me say 2 words about the proof. So for all of these things, that's a complication that you're having to deal with. And it comes up in various ways. It doesn't come up in the same way in all of the proofs, but that's the issue. And the way that we dealt with it here was that essentially, so we have this sequence space, which is not multiplicative, but it's almost multiplicative with these connecting words. I'm going to apply the famous, as I've learned this week, Roland technology. So what you have to do is you have to, this finite length connecting words, you have to add this finite length connecting words, or bounded length connecting words in between everywhere. Where you might want to split things up, you just have to add these connecting words. Okay, so the space ends up looking kind of crazy like this, but then the proofs work. Okay, and so then this was the best that we could do. But now what Ian is saying he can do, he says that he can approximate the singular value function with, for any iterative function system, he can approximate it using a system, a different set of potentials which has this bounded length approximation property, or multiplicativity property. So that's good news after all the bad luck we've had. 7 minutes perhaps. I'm generous with myself. I think we'll be okay. Let me just tell you about another thing. So now, so this was all for this rather mysterious looking, perhaps even unnatural looking choice of targets, these what I call cylinder sets, these dynamical targets. And so then one of the ways in which our paper got rejected, and I'm not bitter at all, was that the referee was saying, but they didn't even do balls. Why didn't they do ball targets? Why are they doing these unnatural targets? And I'm hoping that the referee is in this room, because I'm going to tell you why. We didn't do it because it's very, very difficult. And the question is actually not even the same question. Okay? So this it's obvious. Obviously, you'd want to do balls, because everybody's doing balls, and somehow it just makes you feel like more of a real dynamicist. And so I've had this project going on since 2014 or something, so a good 10 years now. We've been working on, so this is a paper that I'm working on with Thomas Jordan. So we thought, okay, yes, let's do balls. And then we thought, okay, what's an easy case? So this is going to be a very vague statement. What's going to be what would be an easy iterated function system in this affine setting that we could study that would still be, non-trivial and interesting? And so the system that we ended up looking at is this. It's called the Przyducki-Urbanski fractal, and it has two maps. One of them takes the unit cube to this one with proportions 1/2 and lambda, and the other one takes it to this one with proportions 1/2 and lambda. Okay, so that's the iterated function system that we were looking at. And then we put a ball center or a square center in here. So then we have some ball centered at x0 of some radius that we are looking at. The radius that we choose is going to be of exponentially decreasing size, because otherwise we would not be in the zero measure case. And okay, so we're asking about the dimension of this thing. Now, the first complication that you have is that this picture that I drew up there, which is quite nice, and it was useful for us when we were doing the proof, it was useful for us when we were defining the potential dimension number even, it just doesn't happen here because okay, so you have if you're looking at your pre-images of, so you're looking at your pre-images of balls, right, or a ball. This is what you're looking at, right? You want to understand what that looks like. So here again, if you map it to the sequence space, you have your free choice of the first n digits, just like you did before. And then you have the ball, okay? Now, what does the ball look like symbolically? I mean, God only knows. I mean, we don't. It's some sort of a horrible thing. So there's a little bit of a unique choice, and then there's some sort of a tuft that is very hard to understand. Now, the reason why we thought that we would still be able to deal with this, obviously we knew that this was going to be a problem. The reason why we thought that we would be able to deal with this is that when you project this setting, if you project it down to the x-axis, what you get is the Bernoulli convolution. And the Bernoulli convolutions are very well studied by very clever people. And in particular, they have been studying things like, codings of points in the Bernoulli convolution. And that's exactly what we are interested in here. But as it turns out, it somehow still problems remain. Okay? Now, if we were a little bit miffed when Balázs and Sasha improved our result before we had time to publish it, here the situation is rather different. If somebody came and fixed this for us and did it before us, I think both me and Thomas would be relieved, because that would mean that we wouldn't have to write down this horrible paper. It's now like 35 pages long, and there's 12 cases, and the formula splits into 3 possibilities, and like it's all it's difficult. Okay, it's difficult. Even in this very simple setup, it's very, very difficult. And so I don't even. Maybe one day I will be clever enough to do it in this setting of arbitrary affine iterated function systems, but currently I can't. Okay, so that's another unfinished work, but it's not with a question mark. I mean, the proof is there. It's just extremely difficult to write it down in such a way that it would be submittable to a journal. So yeah, it's finished. It's just not published, publicly available. Right, so now I have 2 minutes remaining, and I did want to talk about, I now only just talked about shrinking target sets, and there are different kinds of sets that you can look at on iterative functions. It's not, we can probably guess, because Philip just told you that you can, for example, you can look at eventually always hitting points. He was looking at the measure problem, and so there's a couple of papers, not very many, where the corresponding dimension problem has been looked at. There's a paper by my student, Xintian Zhang, on this. And then the final thing that I want to tell you about today is what is known as a dynamical covering set. So it's also a limb subset. So yeah, it's also a limb subset. Let me just, I'll just use 2 minutes on this and then you can all go have lunch. So dynamical coloring set. So here we're not even able to deal with the affine case. We're stuck with the Fi being similarities, meaning that they scale by contraction ratios. Call them scaling constants, lambda I. We have the open set condition. It's like a separation, the strong separation condition. So let's just put the strong separation condition. Nobody asks any difficult questions. Anyway, so what we do is, and we have some x which is in lambda, and we have the x corresponds to some coding from the sequence space. And then we have some ln, which is of this form. It's of the form log n over alpha for some alpha. And so then the set that we were looking at is this. So we call the dynamical covering set, and it's the limb subset that you obtain when you follow the orbit of x and you put a ball around it at time of appropriate size at time n. So what it looks like is this. So it's the image of lambda under f starting from the shifted sequence at time n up to the ln. Now, why do I say that this is a ball? It's a ball because we're dealing with similarities, and similarities have scalings, so you get a ball. So what did we prove about it? We computed its dimension for typical centers. Quickly write it down here. So this is a theorem. It's due to Balázs and me, Sasha. And it says that if x is Bernoulli typical, then the dimension of this random covering, or this dynamical covering set is going to be given by the value S naught, which makes this happen. And currently, we've only done it for small enough alpha. But it's a work in progress. Okay, I will stop here. Thank you very much for your interest.